Kira Radinsky, Chairwoman and CTO at Diagnostic Robotics. Welcome to the Data Exchange Podcast.
Hi, everybody.
Hey, Kira, so it seems like your background is really well suited for the situation we find ourselves in. So you describe your field as medical data mining, but for our listeners who are not aware, so Kira actually first came to public recognition around the time she was finishing up her graduate school, and she was working on things like disease epidemics, political movements, and basically forecasting some of these things using new tools and alternative data sets. So it seems like a lot of that translates to what we have now, right?
Definitely. So let me tell you a little bit about what I was doing and how we got to actually clinical triage systems in the middle of COVID.
Yeah.
So my personal background, I mostly was building prediction systems, so taking everything humanity wrote since 1851 till today, free text coming from news articles, social media, and building algorithms that can read all of this information, extract patterns in history, and predict future events. So I worked in Microsoft Research, and with collaboration with the Technion, we were able to predict the first cholera outbreak in Cuba in 130 years. We then collaborate with the UN to predict the Sudan riots in 2013. I then founded SalesPredict, which was applying similar algorithms, but in economy, trying to predict economic events for large B2Bs. The company was acquired by eBay, and I've been their chief scientist from Israel for a few years.
So Kira, let me stop you there. So when you say you built these models to predict some of these events, basically you took data that the normal people, the people in that field never even considered using, right?
So I think they did consider, but doing this automatically and just going through the entire hypothesis space was just very hard. And we're pretty much one of the first researchers to actually apply this in scale and show results in actual pandemic predictions. So for example, cholera is a disease that kills 100,000 people every year. But if you identify this in time, mortality rates from 50% to less than 1. And we identified the pattern that if you have a drought and 2 years later in those areas, you have floods and storms, the probability of cholera approximately a month and a half later is very high, but only in very specific countries which are landlocked and with lower GDP.
And so the types of data sets that you used, at some point you started using things like social media as well, right?
That's true. So for example, for predicting riots, we identified that if you have a subsidized product, you stop subsidizing it, people will go to the streets. And then if the police kills one of the young people, then you're going to have huge riots. And we've seen this time after time after time in the Arab Spring. So to predict the Sudan riots, the algorithm noticed that the gas prices were rising, which were subsidized before. People went to the street, a 32-year-old got killed, and there were huge riots for 2-3 weeks. Part of this information is also coming from the social media. For example, the identification that the fact that the gas is rising, people are very angry about this. It's all coming from the social media eventually.
And so the current startup that you have, Diagnostic Robotics, was founded before COVID, but recently it sounds like, based on what I'm reading, you folks have focused a lot of your efforts around COVID, right?
True. So what Diagnostic Robotics does is build clinical triage systems with access to approximately 100 million historical visits, free text inside emergency departments, primary care clinics. And we started building systems that can read all of this information, extract answers to clinical questions, and predict how urgent this patient is, which doctor they need to see, etc. The idea was to eventually to build workflow automation to identify where the patient needs to go, which doctors, and automate a lot of the flows today, especially with the rise of telehealth. And this is where COVID happened. And we were asked by the Minister of Health here in Israel to use our clinical triage system, this time triage for COVID. When it only started, it wasn't clear which questions needed to ask. So in less than 2 weeks, we started running this in a national scale, monitoring 8 million patients on an almost daily basis. They were receiving text messages asking about clinical conditions, and they were able to add free text as well. We started receiving results from COVID tests from the government, and eventually we started building machine learning models predicting what's the probability, given the answers to clinical triage questions, that this patient might have COVID. We were the first one to actually identify that the loss of smell and taste, which was just 3 cases in Italy. Here in Israel, it came up after 3 days. But even things that are today less known, for example, extreme fatigue with dry cough are highly correlative. We are also able to identify this over time, so the symptoms themselves are very indicative on where you are in the disease. So today it triages you, understands what the probability of this patient having COVID, but also what's the probability that this patient will deteriorate. The reason is in Israel that we're building medical setting navigation. If the probability is low, stay at home or go to a COVID hotel. If probability is high, we want to send them to the hospital as early as possible because the deterioration is very fast. Since then, I'll just add a couple of more words, is that the system was also deployed in Odisha, India for 50 million people with collaboration with Deloitte. But we've also partnered with Rhode Island states, and we're today they're a national triage service for COVID.
So a couple of questions. The first is, so the inputs sound like a combination of free text and then answers to self-diagnostic questions. And
so I wouldn't call it self-diagnosis because eventually it doesn't give diagnosis. But eventually the way it works today, it's not a symptom checker. It's just a clinical triage to identify how urgent you are and which doctor you need to see. And Israel will also now connect to the historical medical records, looking at the patient history, which drugs they're taking, etc., to improve our probabilities as well.
And so where does the free text come in?
Mm-hmm. So when we only started, it wasn't quite clear what questions need to be asked. So there were free text answers. It's like, what else are you feeling today?
I see.
We started deriving additional symptoms from that at the beginning of the pandemic.
So how do you, Kira, I'm curious, how do you, what's the process for QAing, testing, reviewing, and validating something like this?
Oh, this is an amazing question. So first of all, when we only started, you have to build a protocol. So there's a medical team actually approving some of the questions. We then show retrospectively that the additional questions that we deployed make sense. Then do a prospective trial. So they actually identify the people we mentioned and do a very specific COVID test with a control group. All of this had to happen very fast. So we actually finished the entire trial period in less than a week. Once we approve this, it changes the clinical triage protocol and it changes for the entire population of Israel in a single day. Another component that we were doing is not only predicting on a single person layer for medical setting navigation, but also building epidemiological maps for the Ministry of Health. They asked us to predict where COVID is going to be in 2 weeks from now. The reason it's needed, they needed to understand where to send the COVID tests, and more than that, how to build lockdowns. So how would they check it? So the first time they even told us, publish 3 cities in the media. Let's see if you can actually put your money where your mouth is. So we published 3 cities. They sent COVID tests, and 2 days later, they put a lockdown on those cities. And since then, on a daily basis, this report is given to the Vice President of the Ministry of Health for decisions. But this is only one solution of data. There's data coming from the different COVID tests, coming from the HMOs, the 911 service, etc. And we're just one funnel of information feeding their decisions.
So in your previous work, as you alluded to earlier, scale was important, right? So you were one of the first people to be able to do some computations at scale. In this context, how much data do you need in order to build a system like what you folks have?
So it depends what. In COVID, the number of exams needed wasn't that high. And the reason is the disease was spreading really fast. So we had approximately 5,000 cases when we only started running. It was enough to train the machine learning algorithm. If we're talking about the general triage system, then you need millions. So today we even have access to 100 billion different historical medical records and claim data to build those models. And the reason is there's a very high variation in different conditions. So the common ones, headache, we're really good at. So we're at AHC of 92 for quite some time. But there's very specific disease that you need enough examples and enough variations of different ages, different races, etc., to get to a really good, precise probability.
So is now that you have like a few months of having the system out there, what further improvements can you imagine? Do you think that what's the so the ultimate thing is to become more accurate is obviously right. So but I guess you can start using more data, or so. What are the other levers that you can pull?
Yeah. So in order for the model to really work well and for us to be able to predict where the pandemic is going to go in 2 weeks from now, so using information coming from people, from their answers to the triage questions, but also from geolocation, car movements, etc., where people are moving from one location to another one. But still, we need people to answer our questions. And this is where it eventually succeeds and fails. If they do not answer, we don't have any indication. And this one is very hard. So one of the things that we started changing in the beginning, people were volunteering. 25% of the population of Israel was filling in the questionnaire at least once a week, with 83 to 89% completion rates, depending on the different weeks. But then the first wave was over. The population said that we don't need to answer more clinical triage questions. We're all healthy. And this is how we started the second wave here in Israel as well. So we had amazing 2 months between the first and the second wave. No sick people, less than 12 people sick every day. And today we're reaching to even 2,000 on a daily basis. So the idea was, how do you make people to actually volunteer and answer this data? So a lot of the changes that we started to do is to make it obligatory. If you want to have access to anything in the healthcare system, in certain countries, you cannot even receive money from the social system without filling in the clinical triage questionnaire. And the idea is we need to really quickly capture this. Israel had 2 ways of trying to handle the pandemic. The first one was based on location. If you're very close to a sick person, you get a text message and you will be sent to sit at home for a couple of weeks. The problem is a lot of people are complaining about the privacy. They stopped it, now they started it again. The second one is clinical, like I just suggested. So the entire clinical triage, identification of areas, and what Israel is now doing, they're marking areas in green, yellow, and red based on the feeds of information coming from our system, from the COVID test results and other information. And the green ones will not have any lockdowns. The red ones will have much more restrictions. And this is why people have more incentives to both answer those things and actually keep social distancing.
So how big is an area? Is it like a city or a city block?
We're running the system for the entire state of Israel.
Yeah.
So the green, yellow, and orange we're doing on a city level based on privacy. They were thinking about moving to a neighborhood area, but then it still has privacy issues.
Yeah, so that's my other question. So with mobility data and contact tracing, so there's always privacy concerns, right? So how do you reassure the public?
Right, so the type of information that we're using is for epidemiological maps. In other words, it's completely anonymous. We just mark the areas which are problematic and which are not. Today, if it's not anonymous, the information is only shown to their primary care physician. In other words, it's only used for clinical output. We do not use their location. They're just going to have a doctor call them and talk to them about the implications of the symptoms they have right now.
So at this point, so when you folks developed the system, you're computer scientists, you happen to have some prior experience in the healthcare and medical field, but to what extent did you rely on domain knowledge and domain expertise?
a lot, right? So during COVID, we mostly built machine learning systems, but we also had clinical protocols. There was already enough information coming in from China, coming in information from Italy to build the initial models to understand which people will deteriorate. The information from Italy was much cleaner for us to actually build the models, and this was the first models were deployed here in Israel. Once we had enough information coming from Israel, we started extending those databases as well.
So domain experts, obviously, in order for them to embrace a system, besides it being accurate, they want to be able to understand how it works, right? So it can't be a complete black box. So is that true in this case? So are the experts willing to tolerate a black box?
No. So a lot of the things that we've seen, especially here, clinicians want to see exactly the questions the public is being asked and how decisions being made. And it's not only about clinicians, it's getting a lot of the trust from the public. If you don't know which symptoms are causing what and what exactly to do, you will not trust the system in general. So what the system done is just create combinations of hypotheses. In other words, combinations of symptoms with high probability for a certain disease. And then based on those, it would approve this or not in a protocol. So eventually there's a set of rules mined from historical data.
So how do the policymakers consume this information? Is it dashboards or?
Exactly. So we started with dashboards. Unfortunately, nobody had time to look at dashboards and play around with them. So they only get a fine report with 10 top cities, 10 good cities, and that's it. But they also have a full map and indication of us of what's the probability of deterioration in 2 weeks from now.
So are there examples where the system vastly underperformed and you folks were able to chase down what happened and then basically make updates to your system?
Of course, we had a lot of, so in the largest cities, we had approximately 73% precision. In other words, we were able to predict which, so it's precision in 10. Out of the 10 cities that we would predict, approximately 7 till 8 would be correct. We always have problems with the smallest cities. One of the main reasons for this is the high variance. We might have even 30 people answering the questionnaire. Okay, you would never actually capture the sick people. There was a lot of bias in how they would answer. So sick people would not answer, only the healthy people would answer. So we actually had to calibrate based on the historical information on how many sick people are not in those areas and then identify the bias in certain cities.
So do you think there's a better UX than just asking questions? So is there like a, here, point your phone to yourself and the phone will...
So let's talk about medicine in general, right? 75% of the diagnosis is done by asking you questions.
Is that right?
Yep. So the rest is a physical examination, which many of the times are not even, so 50% of the primary care meetings are ended without a physical examination. The rest are from sensors, but this is only the top additional 10% of addition. So today there is not a lot of things that can be done and listen in healthcare without asking you questions of some sort. We can look at your history. So for example, one of the projects that we've been working is proactive healthcare.
What about my smartwatch?
Yeah, the smartwatch is not clinical grade, so it cannot say many things. Well, it's a nice toy. It makes you be more active, and this is why it makes you healthy, which is really good. But doctors still didn't find what exactly to do with it, right? There's very specific centers which are FDA approved, which you can use in order to make clinical predictions. Not all of this area is eventually regulated. So I agree with you that you can look at your phone, but the phone eventually is going to see what it's going to see. If you are pale, it can see some DNA features. Let's say your relatives do have some genetic disorder, but most primary care problems are not about the DNA disorder. Okay, they're not about being pale or not. If somebody is so pale and cannot answer, they're not even going to answer our clinical questions as well, and they're not going to point their phone to their face.
So there's also, I don't know, Kira, to what extent you follow, there's also the group of people who build the models that the policymakers use. These are the kind of the models for the spread of the disease, which I imagine is kind of the stuff that you used to do. Um, does your do you folks cooperate with those group of people?
So unfortunately, we did not collaborate.
Yeah.
The models that we used were mostly ensemble models, trying from each city to predict for the cities next to them what's the probability that in 2 weeks it's going to spread. And eventually, it's a very exponential disease. So there's very specific exponential models that you had to fit to actually be very precise in those. I think a lot of those things is around certain events which we knew that were causing. So a lot of events with a lot of family gathering. I think that maybe getting an additional vision image about seeing crowded areas with a lot of people actually might increase this information. We wouldn't get this information from walking of people, some data that were received. It wasn't as precise as you would love because not everybody would opt in to actually contribute this data.
So what's your sense of so since in your previous life you used social media to do some predicting, is social media useful in the context of COVID?
Right, so this is very interesting. There's several works that were trying to predict flu outbreaks based on social media. For example, if I'm tweeting that I'm sick, high probability I'm sick, so people that are following me have been with me in the same geolocation might also be sick, etc. So several models similar like that could have been built for COVID. However, I've never seen a work on this topic, and there's much more direct options than just mining geolocations on Twitter for that one.
So besides aggregating data, so what other privacy preserving tools and techniques and tricks do you folks use?
Well, we use the simplest trick. We don't keep any PHI data.
I see.
Okay.
I see.
So eventually we have answers to clinical questions. All the PHI data is saved on the healthcare system servers. And eventually we just exchange the predictions from one place to another.
And then you report at a higher level. I guess once you start saying people in this square mile, then it becomes a little trickier, right?
Exactly.
Yeah, it depends on the density, I guess.
Yes, and this is why we're not predicting on a neighborhood basis, but mostly on a city level.
So I don't know to what extent did you work on disinformation in your previous life, but COVID in particular is rife with disinformation on social media. So is that something you follow? Kind of the information propagation in general, right? So how information propagates.
So I do read papers on top of this. I'm not the best expert. I've been doing lots of work around temporal graphs, trying to identify anomaly in those graphs. However, we did not attempt to use those on healthcare data specifically. We're trying to identify anomalies in epidemiological studies, but this is very early on in our research.
So what's your sense of so set aside vaccine. Let's say we don't have a vaccine. How do we see each other in conferences again? What's the end game here, short of a vaccine?
Right, so there's several things that need to happen. And actually the history of this specific disease is very intriguing. So similar H1N1s were developed in the past, and then came H2N2, which kind of made the previous one just disappear. It came back just a little bit with the swine flu, and then with another flu, but then it was contained in the areas because it was so brutal, it would kill the host. And when it could kill the host, it wouldn't spread as fast. And here it comes back again. So either we're going to have a vaccine or we're going to have a virus like H2N2 have done to H1N1 that's eventually going to take their place. Another direction that I'm thinking that might be very interesting is everything around drug repurposing. So here in Israel, we had access to approximately 4 million medical records. So 4 million people's lives for more than 20 years. Based on their information, we're trying to see if somebody taking a certain drug but it's getting better in other diseases that they had. And we started just running different machine learning models on top of this and identified amazing things. For example, a family of drugs called PPI was actually reducing hypertension, but we couldn't explain why. So we had doctors sitting, reading publications, eventually thinking about hypothesis. And then we decided to kind of automate the process. We built a system that can read medical publications, approximately 19 million medical papers, and based on those, trying to explain any correlation in the data. If we identify correlation, we show this to the expert, and then they can do a clinical trial. So for example, the explanation for why PPIs help is if you have a heartburn and you have PPIs, which is eventually treating this, you will sleep better. If you sleep better, you have lower blood pressure. So this was the explanation written by the system. And then we started to identify other drugs which are not improving disease, but actually causing them. So we identified correlation between people who are taking beta blockers and the probability of Parkinson after several years afterwards. So we've seen 40% increase in probability. And we've done matching, so other things like ACE inhibitors, et cetera, did not have the same effect, which is fascinating. And the algorithm here found another paper which showed that asthma, which is kind of working very differently than what beta blockers, it's the nemesis of beta blockers, let's say, have actually shown that it actually improves Parkinson's. So we've seen the same thing that was shown in mice in the past, this time in the human body. The reasons we didn't know about this, it would take 15 years to develop Parkinson's, you would never actually connect this to the family of beta blockers. By the way, 25% of the population above the age of 50 is taking beta blockers in some way or another.
Oh.
So my question is, and this is a lot of the things that we're seeing right now in COVID, people are identifying drugs that can be repurposed specifically for COVID. So 3 things might happen, right? We find a vaccine, perfect. We need to contain this just like we're doing right now. Or finding a solution, a drug that actually going to shorten the time people are spending in the hospitals, like they're already doing right now, which is going to make it more durable for the health system. So even if we don't keep social distancing, the health systems will not collapse.
Right. So by the way, so as you were talking there, I started thinking, so one of the things that makes medicine challenging compared to advertising is that you have to really be careful about making the leap from a correlation to something else, right? So you really have to understand some basic mechanism before you make a recommendation of a course of action, right? So how do you protect yourself against jumping to conclusion because you might have found some correlation?
Mm-hmm. So there's no simple answer, right? So the first thing that we're trying to do is either validate this based on evidence-based or just find several explanations that would make sense. Eventually, in all of those things, you need to do prospective trials. Give an example of something very interesting that we identified, that out of all of the people coming in with chest pain into the emergency department, 25% of them will say it radiates to the left. The problem is the doctor will agree with only 5% of them. So this is a big gap and a distribution shift between what we trained on. So we trained on medical summaries written by the doctors, but eventually it's being applied on patients answering, which is not exactly the same distribution. And a lot of our work is getting to the fact that this distribution look alike, that the questions that are answered by the patient are very similar to what doctors perceive when they wrote these questions, which is a huge gap in between.
So one of the things you mentioned at the start of our conversation is free text. And as you know, there's a lot of developments now in NLP. And by the way, for our listeners, Kira is actually going to keynote at a conference I'm chairing called the NLP Summit. So what makes reading text in the context of medicine harder? Can't I just use some magical neural model or GPT-3 or whatever? I mean,
Of course you can.
how
It's just more.
how much tuning do I need to do?
Right. So to get some results, right, you can use whatever deep learning you have, you can train it. You need to remember that medical summaries are not natural language, it's clinical language. Okay, they're structured in a different form. The spelling mistakes are even different. It's written in a way that to communicate some information from one another. So this is actually making this a bit easier because it's structured. It's more structured than one would think. The problem is the type of mistakes there are crucial, right? So if somebody says that it radiates or doesn't radiate, left or right, and if you don't get those things right, you cannot make a diagnosis. So a lot of those things in scale are very problematic. So we find ourselves eventually thinking even on the label. Did the neurologist give this diagnosis or the ED doctor gave it after they were 28 hours inside the department? Who's right? Sometimes you don't even have the same diagnosis. One of the things that we have identified is that if the doctors disagree, how do you choose the first one? So usually they would say, hey, just take the expert. But then we can actually see the different tests being done afterwards. So the labeling itself is a huge problem. One of the problems we've seen in Israeli medical summaries, they do not give you the diagnosis in structured form. They write it somewhere in the text.
I see.
But it's almost impossible to understand this. You have to actually infer this. So even the diagnosis itself, which is your label, needs to be inferred from the text. And just learning this from free text is not enough. You need to use the structured tests, results of lab tests that are coming in to actually get into the head of the doctor about which diagnosis they were thinking about.
Which means when you took your system, you alluded to earlier, you took your system and have it deployed somewhere in India, but now we're talking about different languages.
So what we're doing right now, we're trained this on data coming from Israel and the United States. Once the model is trained, luckily now the human body is very similar in all of the world. So we deploy the trained models. We just need to build the mapping between from our answers to the local language. So it's mostly translation of the features, but not retraining of the models for specific populations. However, things like dengue disease, etc., which are not common anywhere else in the world outside, for example, Asia, have to be trained again. And if not trained, like we do with COVID, when we didn't know anything, we just write rules which are common from the clinical language, and then you start learning as you go.
So, but that even that taking the model and then understanding the local language. But as you said, we're not talking about human language. We're talking about medical language. So there's some sort of specialization and domain knowledge involved, right?
So 1/3 of the company are clinicians eventually.
I see.
So we build combined teams of data scientists, engineers, and clinicians for almost each task.
I see. I see. Well, this has been a great eye-opening conversation in terms of the stuff that you folks are doing and the impact that you are making, particularly since you are able to actually, it sounds like, impact public policy.
Oh, well, wish we could have been able to impact it even more, but doing our best. As I mentioned, we're just one funnel of information in a very complicated decision-making process.
Yeah. And so it's you have to actually have decision makers who are willing to use the information that you present them, right? So
luckily enough, we were collaborating with very innovative ones that were willing to take the risk, and now the system has been proven as the right way of making decisions and has been adapted in several areas in the world, even if not done by our company.
Perfect. Well, thank you, Kira.
Definitely, and thank you for having me.